Visual motor coordination using quantum clustering. This will be the topic today. Last class we discussed also about the visual motor coordination using a different technique, that is the Cohen sum self-organizing map. Today we will present a different approach, will be a little more introspective. It may be a little difficult for you to follow, but just go through the class. You may be interested to do something interesting in this area if you have liking for it. So, this is the 8th lecture on this component neural control, which is the module 3 of our course on intelligent control. So, visual motor coordination using quantum clustering. Presentation outline. We will be talking about quantum clustering. Earlier we did the clustering using Cohen self-organizing map. We have also discussed what is meaning of clustering in general notion of clustering. Now we will be talking about quantum clustering, the motivation, the algorithm, general results, and then we will apply this quantum clustering to visual motor coordination, which you have already discussed in the last class. The problem of visual motor coordination using quantum clustering, a training algorithm, comparison with Cohen sum based algorithm. So, quantum clustering and overview. Those who want further information about the quantum clustering, I would suggest that you please read the paper by David Hearn and Asaf Gottlieb, the paper published in 2001. This particular quantum clustering algorithm is motivated by scale space algorithm using a Parsons window estimator. The scale space probability distribution is the solution of the Schrodinger wave equation with a potential function Vx that has a similarity to the cost function. You know that this when we do any kind of clustering, so this is our cluster center and this is the data points, and we try to always minimize this cost function. We always try to minimize this cost function. To let you know, let us see, this is my workspace. If it is a 2-dimensional workspace, and if I say these are some data points here, some data points here, some sparsely data point there, and a lot of data point again here. So, obviously what I would like to do is that I would find one cluster point here, another cluster point here, another cluster point here, and maybe another cluster point here. So, what is the objective? So, this xjc is the cluster point. So, this j would vary from 1 to 4, and xi is all the data points. Xi here represents all the data points. So, what we are trying to find out is that how far are various data points from these cluster points, and the objective of clustering is to minimize distance, this distance, this the xjc minus xi. So, I hope you understand xi represent all the data points in the workspace, sorry, in the data space, and xjc are the few clusters that we have selected. In this case j is 1, 2, 3, 4. So, 4 clusters, and the clusters must be selected in such a way that this particular cost function is minimized. Okay. The minimum of the potential function Vx describes the cluster centers. So, what we are trying to do is that, as I said in Cohen network model, that given a workspace, given a data space, what we try to do is that we have innumerable data, a lot of data, and we try to represent those data with minimal representatives. And this is the whole purpose of a clustering is to how to find these cluster points, and that we saw that how we solve that problem using Cohen self-organizing map. Scale space clustering, you can refer to the papers by Roberts, which is published in 1997. Given a set of observations from the set S over a d-dimensional space, S defined as x1, x2 until xn, a non parametric estimate of the probability density function of x belonging to S as the weighted combination of a set of basis function f I or kernels evaluated at each observation x I, which is this is the probability and given as w y f I x. So, that is that what is the probability distribution by, or you know, when we look at the data space, what is the probability that data is likely to be at a specific point in the data space. On considering the Parsons windows approach, where the weight w I is independent of the position, and then modulating the above function with an optimal filter with scale S k s x, we get the following, okay, which is of the form is this is how the probability distribution function for scale space clustering. For the estimate to be valid probability density function, the function psi I x must be positive symmetric function, and a popular choice of this is a Gaussian filter. So, what is normally done is that given the cluster points, as I said, so how do I find when the datas are everywhere where you are seeing, and to find out a cluster point that represents the data. So, we have a Gaussian function, okay, e to the power minus x j c minus x whole square, okay, by 2 sigma square. So, this is the normal Gaussian function, and what we would like to do is that we should maximize because you see that when this is minimum, earlier I said this has to be minimum, this is minimum means this exponential function to the power negative, obviously that would has to be maximum, okay, if this is minimum. So, ideally this minimum should be 0. So, then e to the power minus 0 is 1. So, that is maximum value. Okay. So, quantum clustering, the algorithm at time independent Schrodinger equation is defined as h psi, h is the Hamiltonian, minus sigma square upon 2, this is the gradient square, plus V x psi x is E psi x, where psi x is the eigen function and E is the eigen value. Given V x, the potential function, Schrodinger equation finds, this is Schrodinger equation, finds the psi x or the eigen function. In quantum clustering, psi x is assumed and V x is found out. Normally in Schrodinger wave equation, what we do is that we supply the potential function and we see what is the psi x, okay, psi x, but here given psi x, what is V x, that is found out, or QC is an inverse process. Considering Roberts probability distribution as the wave function, psi we have the following. So, we assume our wave packets to of Gaussian nature, okay, this is a Gaussian nature. So, following scale space clustering approach, the maxima of the above wave function gives the location of the cluster centers, that is the ground state of Schrodinger potential gives the cluster centers. Okay. So, the maximum of this is the cluster center. The same way we can say the minimum of this is also cluster center. Potential function, how a potential function looks like. If you say that iris flower problem is a 3 class problem with 4 variables. Here the 3 classes are shown in 3 colors, red, blue and green. The potential function is plotted for every instance or data point. While iris setosa is linearly separable, the other 2 classes are non separable to each other. Okay. So, you can easily see that in this case the setosa is the red one, and there I can place a line by which this is separable from other two classes, but I cannot actually put a line because this is. So, this is not a line, this is a so this is potential I have plotted for each data point, and the potential function V x, and I am plotting for V x for every point, and then I am trying to see what we are trying to do is that you get raw data. So, you have to map them in such a way that each class of data can be separated, they are occupying different zones. So, if you look at the raw data, so they are all mixed, okay, but by doing some kind of operation on them, can I separate those classes? This is the point of clustering. Now, potential versus wave function. As we said, the normal approach is to find out, we create the Gaussian mixture model of the data points, and while trying to find out the cluster points, we try to find out what is the maximum, or we maximize this Gaussian mixture model while deriving the cluster centers, and we showed that this is same as finding the minima of the potential function. Okay. So, the plot of potential function and the wave function shows that maximum of the wave function are not so clearly defined as the minimum of the potential function, which can be found in every cluster. So, this is actually the minimum, okay, and this is the maximum points of the same iris data that we talked about. So, you can easily see that here the maximums we can find here over various data points, but in this there are we can't, because if I put a threshold here, these minimas maximas will appear, but in case here if I put a threshold here, I am getting all these cluster points because they represent the minimum values. So, similarly, if I go on, but here we have to compromise a lot to find some cluster points here. That means I have to put a threshold in this level. So, while putting threshold in this level, you are compromising, that means all data here remains under the cluster point. So, what we are seeing is that if I put in the previous case a more reasonable threshold, then the cluster points from using this is wave equation, this is wave function, and this is the potential. So, what we are trying to do is that for every data point we are computing what is here the potential function, okay, using the formula, and here we are finding out what is the Gaussian mixture model function, okay, that is the Gaussian function. We compute that for each data point and we plot them, and there is a fluctuation. So, how do I find a cluster point? I find that is a cluster point for which the potential function is minimum here, and in this case the wave function or the Gaussian function is maximum. So, if I put a threshold for this wave function here and threshold for the potential function here, then what I am trying to get that over the entire range of the data I have cluster centers. Here is one cluster, here are 3 subclusters, here are 2 clusters, and here are multiple clusters. Okay. Whereas, if I look at the wave function side, so I have only clusters in this zone. So, I have no cluster in this zone. In this zone I have no cluster. Okay. This entire zone is unrepresented. So, quantum clustering, given psi, the potential function V is given as V x is E, which is eigenvalue, and sigma square upon 2 gradient square psi upon psi. If V is 0, that the minimum is 0, then we have E equal to simply minus mean grad square psi upon psi. Since psi has no node, E is the ground state energy of V. Also V being a non-negative function, E must be positive. So, this gives E between 0 and d by 2, where E equal to d by 2 is the lowest eigenvalue of H determined by harmonic oscillator problem. So, the quantum clustering implementation. Now, this is our wave function, which is a Gaussian function, where q is 1 upon 2 sigma square, because this gives the width. So, the initial estimate of the potential function V x is evaluated as minus d by 2 1 upon 2 sigma square psi sigma I x minus x I whole square, and this function e to the power minus x I whole square by 2 sigma, which d is the dimensionality of this space. Evaluate E equal to minimum of negative of minimum of V x, transform V x to V x plus E. The data points that are minima of the potential function V x, which is equal to 0, then denotes the cluster centers. Okay. So, we just add this E to find out what are the cluster centers. So, in essence what I said is minima of the potential function V is same as maxima of the wave function, and based on that cluster centers are decided in quantum clustering using the minima of the potential function. E sets the scale on which the minima or the cluster centers are observed. So, that threshold, where should I put the threshold, that is selected by E. So, by that you see that what we did earlier concept wise, that where do I put this thresholds, here or here. So, you see that if I am putting threshold the low value, I have less cluster, and the moment I increase more and more, I have number of clusters more, right. So, this is the point. So, this is adaptive. So, depending on E, where our cluster centers will change, and E will depend also on the 1 upon 2 sigma square. So, the only parameter which needs to be varied is the width of the parameter q, and q is 1 upon 2 sigma square. So, higher q value gives more number of clusters, obviously. Okay. So, we want more number of clusters, so you increase the value of q. Okay. So, here an example. So, if you look at here the iris data set, first two principal components if you plot, then you have these three different classes. So, you see that one class is completely separable from other class, but whereas these two class, they are all mixed. So, we have to create a method by which I can linearly separate the green from the blue. So, the iris problem is a 3 class problem with 4 dimensions. Considering the first two principal components, a distribution as shown above is obtained. But now by mapping these data points, by transforming these data points through their potential function and the thresholding, V is the potential function, this is V by E. So, E decides the thresholding and V is the potential function. If you do that, so you can easily see that I have a line here that separates this class from this two class. Okay. And similarly, I can also put another line here that separates the green from blue and red. So, you can easily see that these three classes are now distinctly separable. So, the three classes are very well separated in V space on clustering in normalized 4 dimensional input space. Note that classes Virginica and versicolor are totally non-separable classes, but are very well separated here, that is the red and green. Now, if you look at the previous one, sorry, red and blue, they were unseparable, and now red and blue they are completely separable. I can put a line by which they can be separated. So, giving this idea about what is quantum clustering, now we will apply to visual motor coordination. We have introduced some new concepts also to this visual motor coordination in this particular lecture than what we discussed in the last lecture. So, the visual motor coordination, as I said you earlier. So, you have a robot manipulator here, and this robot manipulator, the end effector is being observed by two cameras sitting there, camera 1 and camera 2, and you have any target, you have any target point, and this end effector wants to reach this target point. So, target point is also in the camera focus, so also the end effector. What is the objective is? The objective is how do I reach this point, target point, through learning. So, you imagine when I am holding a pen here, and this hand of mine wants to reach that point. So, this is a visually guided motion, and in this visual guided motion I am least aware of the arm dynamics. I really do not take into account of any kind of dynamics for my hand. Okay. Rather, it is the mechanism is such that it is by method of a kind of a learning mechanism, that how do I guide my hand to a target point. If you see a child, how he learns as he grows by various trial and error methods, similar kind of situation which we say hand eye coordination, that many things we do very dexterously simply by hand eye coordination. So, that is the idea here, which is the manipulator. So, in detail dynamics here. So, what we have is that we have three joints, one is the base here, this is the joint for the first link, and here is the joint for the second link. Okay. So, this is the base link. So, base link, first link and second link. So, this is a 3-link manipulator. The 3 joint angles of the manipulator are to be determined for a given end effector position u. So, what I said is that what this coordination principle is, camera finds the end effector position. So, camera always, even if you take a photograph of a 3D point, camera has only 2D point. So, it has u1, u2, say camera 1, and camera 2 is u3, u4. So, you have this 4-dimensional input vector for a given target, a given end effector point, and given the target, what is the objective is that the control algorithm should find out what should be theta 1, the base angle, and theta 2 is the joint angle 1 and 2, such that theta 2 and theta 3, such that by orienting theta 1, theta 2, theta 3 properly, this end effector will exactly reach this target point. So, what we are trying to do is that so there is what we are trying to do is that we are trying to find out from u a map of so theta is f of u. Okay. So, we would like to find out what is theta given u, what is theta given u through learning. Not see, one can use easily the inverse kinematics of this manipulator and can find out, okay. But this principle is different. We do not want to go to the manipulator inverse kinematics and simply learning. I want to find out what is theta equal to fu. The objective is that this is just a curiosity that how learning can be so powerful. We can ignore the inverse kinematics of an actual model and still we can reach any point in the robot workspace. So, what we do is that this fu, or what I have written here is a function of u in this case. This can be linearized, around a specific locally it can be linearized as this particular formula, which is in a local zone. If I know theta s corresponds to this point in the Cartesian space. Okay. In the Cartesian space, this point corresponds to theta s, right. So, then any point near to this Cartesian point also will be very close to theta s. Thus, we can find this expression, we can find this relationship by simply linearizing this nonlinear function, okay, around theta s. So, this is linearized around theta s plus a Jacobian matrix, which is obviously 3 by 4 matrix, and U is the input vector. Input vector, actually input is not x y z, this is u1, u2, u3 and u4. It is just written here 3 because u represents this Cartesian space, but this is actually the input coming from the camera. So, this is 3 by 4 and this whole thing is the u is the actual input, that is the actual data point around this solid point, the thick dot, and Ws is the neuronal center. That is, when I localize or discretize this entire workspace as we did in the Cohen and Sum algorithm. So, when I create a discrete cell, each cell I assume to be representative is represented by a neuron. So, that neuron is associated with a specific Ws. So, what is meaning of that? This Ws actually corresponds to this theta s. Okay. This Ws is exactly corresponds to this theta s, and if given any other point u very close to Ws, how do I represent the exact theta? So, this is my actual theta. So, my actual theta is, so to make it very clear, what I say, let me again make it very clear here. What I am trying to say here, that this is my a local zone in which I have a special point, a point in the 3D coordinate, and corresponding to this coordinate I have theta s as the actual joint position, theta 1, theta 2, theta 3, they take this and a factor to this point, okay. And this point has its own representative in the camera coordinate, which we can say to be Ws. Then we can write, given any point which is very close to this point in the Cartesian space, then the joint space theta can be written as theta s plus as u minus Ws. So, u represents a new data point around the old point, which is Ws. Okay. This is the meaning of linearization. Okay. Linearization around a small workspace. What we are now doing is that we have an input space, we have an output space. Input space is 4 dimensional actually, but anyway we can, because the dimension is anyway 3, but through 2 camera coordinate system we get 4 points. The dimension is although 3 Cartesian dimension, but we get 4 points. Here output space is theta 1, theta 2, theta 3. So, if I really create a joint, this is called joint input and output space. Okay. So, this is u transpose theta transpose transpose. So, this will be a, in this case it is a 6 dimensional vector. A new space is obtained by concatenating the input and output space. We now work in the 6 dimensional space, determine the vector G and cluster that space. You see, the last class what we did, we created a cluster only in the input space. Now, we are creating cluster both in input and output space. Okay. So, we created a cluster. So, we have a workspace and in the workspace that input output space we divided into small center cells. So, clusters in the 6 dimensional space are made up of position and joint angle values. So, corresponding to each spatial position W, we have a specific theta, okay, W theta, and like that we learned this cluster, and these clusters are obtained using quantum clustering technique rather than the coherent self organizing map which we learnt last class. So, cluster centers are obtained using quantum clustering and are combination of neuron centers and the 0 order term. The idea is to discretize the workspace U into non overlapping region F s. So, these each one we say as F s. Okay. So, these are all small discrete cells. Okay. W s belonging to F s is the reference or weight vector for each discrete cell. So, this is your reference vector associated with each discrete cell. Present method use only the input space discretization and no output space information. Earlier what we discussed is that the coherent self organizing map. We also using coherent self organizing, we can also incorporate this. It is not that this is the only, this is independent of whether you do quantum clustering or coherent sum. This is not a defect of coherent sum, it is just that we are utilizing that feature here. So, in our approach we have used a joint input output space partitioning scheme. So, here you can see that this is my 3D workspace in which the robot is working in this, all right. So, and any random point in the workspace the robot manipulator can reach, and correspondingly we have a corresponding to each point in joint space we have a specific theta 1, theta 2, theta 3. But if I look at the output space, in output space if you look at the data points they are not uniformly distributed like here. So, the output space is well separated. What does it mean? This is natural because not all joint angle values are allowed. When I manipulate my hand, possibly certain angles I cannot probably create, or certain angles are not possible, just like also in case of a robot manipulator. So, thus a partitioning scheme with information from input and output space would work best. So, what is the first part then? Perform quantum clustering on the 6 dimensional space formed by combining the end effector position and the joint angles. This gives a set of cluster centers. Each cluster denotes the receptive field of a neuron. These cluster centers are then separated into neuron centers and 0 order term and initialized to the neuron. The initial parameters are not random, and this speeds up the learning space process. The neuron centers and 0 order term need only a fine tuning. The Jacobian matrix needs to be determined. Collective training scheme is adopted. What is meaning of this? That we create a cluster. Through clustering we find out W s as well as theta s. Okay. So, given now theta s and W s, okay, and with new input u, how do I learn this A s? Not only that, how do I also refine the relation between theta s and W s? Okay. So, this is the key question that is being asked. So, what is the objective of this training scheme? I will just explain to you. So, for example, this is my robot manipulator, this is one link, this is another link, and this is another link. Okay. Now, say for example, we have to come to this target point. So, what happens, the learning mechanism, that this algorithm gives some random theta 1, theta 2, theta 3 to this in the beginning when it was not learnt, theta 1, theta 2, theta 3 to joint and to various links, and then the end effector goes to some point. Now, the approach, the learning principle is that how can I with some minimal steps I can bring this end effector like this. So, something like that I can bring from this point to this point through training. So, what is happening here, you see that I have many neurons now in the workspace, and these neurons are actually a 3D lattice. What we have done is a no, actually in the case of coherent network it is a 3D lattice, but in case of quantum clustering we do not create a lattice kind of thing. But what you see is that we have this scale this neurons, and each neuron represents a specific discrete zone of the input output space, and while clustering you have already the coordinates associated with this neuron is ws and theta s, right. The once clustering is done and for each neuron also the AS is defined, then obviously given a u, each neuron output will be theta s plus AS u minus ws, that is by each neuron. But in case in this approach, as we also did earlier, that we instead of allowing only one neuron to take a decision, we allow a group of neurons to take decision, which is says collective average output. So, that collective average output is that this k represents each neuron, okay, and this is within a specific neighborhood, and this h is the distance, in the sense that for example, as this is also a competitive network, that is given input a specific neuron is the winner, okay, according to cluster. So, the winning neuron will have a maximum role to contribute to the, or it will have maximum say to contribute to the decision making process, and others will have less and less say. So, each neuron is associated with 3 parameters, and the output of each neuron is this. So, if this is the winning neuron, so then the maximum to decision making process, the maximum contribution comes from the winning neuron, and lesser contribution as the neurons are away from winning neuron, their ability to contribute to the decision making process dies down, means their participation is to the degree how close they are to the winner. So, this is then the collected average output given input u, given input u target. Okay. So, this distance is a distance of, you can easily see here, mu is the winner and k is the specific neuron, what is the distance between them, and so we also put these neurons in a lattice and then we find out. So, this takes the end effector to a position V naught, needing a correcting action determined by this theta 1 out is theta naught out, which is the initial, plus this is the correcting, that is instead of W k we now put it here V naught, okay, and now the end effector is at a position V 1 and we do not wish to give further correction to it, okay, because if this takes it to V 1 then we do not need. So, the learning scheme is actually the stochastic gradient descent, okay. So, where you can easily see this is all delta V is V 1 minus V naught. Actually, I discussed all these things in the last class. Theta out is theta 1 out minus theta naught out. This theta out theta naught out minus theta k out because this is a kth iteration minus a k V naught minus W k and this is the update law for the Jacobian matrix, which is the norm delta V square, this delta theta out. You can actually derive this algorithm from using gradient descent and so finally the each weight of the neuron is updated as W k using, you see that clustering algorithm W k sorry, just like we did in the Cohen clustering algorithm. So, W k is W k plus epsilon h mu k u target W k, theta k is theta k plus epsilon dash s dash mu k delta theta k. So, this is what you are seeing is that my new weight associated with a neuron k is the old weight associated with the neuron k plus epsilon is the learning rate. This is the distance factor, because how far is the kth neuron from the winning neuron, and u target minus W k. This is a normal learning that is done in clustering, and similarly also for theta k, the old theta k plus the new learning learning rate, and again another distance function and delta theta k, and similarly also for the Jacobian we train with old Jacobian. So, you see that in the beginning, this is the beauty of this entire learning process, as I said earlier also, that we start from no idea absolutely. Our neural network possesses no knowledge of the workspace. Everything is initially randomly initialized without taking any consideration what should be the, what is the workspace size, nothing is taken into consideration. But the moment you give the data, the moment the neural network is associated, sorry, is excited by the data, the learning starts, and then beautifully the automatically the mapping of the topology of actual workspace and gets mapped to the neuronal structure, and a nice mapping results. So, this is a distance measure, the various distance measure. So, mu denotes the winning neuron, the neuron which is closest to the target. The parameters epsilon, epsilon dash, sigma, sigma dash, sigma mix vary during the training time depending on the current iteration using the general expression. So, that eta is eta initial, eta final upon eta initial L by L max. This is the iteration. Okay. So, you see that when I have not started the iteration, so then this is 0. So, eta is eta initial, because this to the power 0 is 1, and when this is L is L max, then this is 1. So, this becomes eta final by eta initial cancels out. So, eta is eta final. So, you can easily see that eta in the beginning is eta initial and eta is eta final at L equal to L max, and this is L equal to 0. Okay. The neurons are indexed by normalizing their weights and in general are not integers. The indexing scheme uses the information of actual position rather than simply associating an integer. So, now we would compare our results today to the last class what we discussed. Last class we talked about Cohen self organizing map based methodology, where we had a fixed topology. In the beginning we fixed the neurons, and fixed topology has to be pre-specified for the workspace, that the number of neurons must be decided a priori. This leaves very little flexibility. One has to begin with random parameters, thus making the process slow. Does not use the joint angle space information when partitioning the workspace, but this is not the this is not only confined to the Cohen sum. This is an additional thing, because for Cohen also we can do this. But today's class what we learnt is that a flexible topology of the workspace is adopted as the width parameter in quantum clustering is changed and number of clusters changed. Quantum clustering helps in designing the workspace topology and no random initializations are done. Uses the joint angle space information when partitioning the workspace. Again, this is not exclusive to quantum clustering, this and this can also be in the quantum clustering. So, this is how we did. Our workspace size was 20 centimeter into 30 centimeter into 20 centimeter. Okay. The parameters, initial parameters were taken as like this. So, at the beginning, 1 up q is q that is 1 upon 2 sigma square. So, this was fixed as 0.12 and then 164 clusters or neurons are obtained. So, these are very few as compared to k sum based method, where 336 neurons are considered. Okay. In the last class we said that in a Cohen cluster 7 into 12 into 4 that many neurons were considered, but here it is only 164 clusters. A mean square error of 0.18 mm is achieved using 164 neurons when 200 random points are evaluated in space. This is significantly small as compared to 1.18 mm using k sum based approach, where 336 neurons were used. This is the result that we achieved, we showed in the last class using Cohen quantum clustering algorithm. Here it is the average error and number of iterations. Okay. And so, what you are seeing is that the errors almost in 200 samples iterations, it goes to is almost decays, whereas normally in Cohen clustering it takes 5000 iterations. So, you see that in this quantum clustering I have put this is the average error and the number of neurons. So, you see that this is an adaptive and a flexible topology in the case of quantum clustering, where number of neurons are not fixed in the beginning. That means, how many discrete cells the original workspace should be consisting of, we decide in Cohen self-organizing map, but in quantum clustering this can be varied by varying the q, which is 1 upon 2 sigma square. So, you see that if I increase the number of neurons, naturally the average error decreases, okay, and this is what is the profile. You increase more number of neurons, the decreases. Okay. So, and this is another interesting piece of results that we derived. We found that this is the number of iterations you require for training, and this is the number of neurons. Okay. So, you see that if you increase the number of neurons more and more, the number of iterations required becomes pretty large. So, you really have to pay a price for making this such a situation. So, that is if your number of neurons are small, you have a very less time, less number of iterations required. So, increasing the number of neurons also needs more time. What you are seeing here is that we commanded the robot to the end effector of the robot to track a circle, and what you are finding the star positions are actually the points along which the robot has moved. So, the average error in tracing a circle of radius 50 mm is 0.0907 mm using 164 neurons. So, star is the track trajectory and the broken line is the actual trajectory. So, a circle is tracked with an average error of 0.09 mm in the workspace using 164 neurons. So, now this is a sphere, and you see that the actual position is the red point and the blue point is the tracked position. So, obviously, we have placed the red point in the first and the blue point. So, wherever you are seeing the blue points, obviously the tracking is perfect, and wherever the red is there, tracking is not so good. A sphere is constructed with an average error of 0.116 mm in the workspace. That means, our end effector is able to reach all these points in the sphere, okay, with an error of 0.1116 mm after 5000 training steps. So, finally, to conclude, we presented a new method of visual motor coordination using quantum clustering, in which the flexible topology, that number of neurons can be increased or decreased depending on the what accuracy you want, what time, because we saw if you want more accuracy, number of iteration increases vigorously, and the reduced number of neurons can give you equivalent results, even much better results with as compared to fixed Cohen sum and joint learning scheme. That is, we proposed that let the clustering be done in joint input output space instead of only input space. So, with that I thank you. After this, what we did is that I gave you some dynamic model in the beginning, and we discussed some control mechanism, and the last two classes we had little a different application of learning methods to control, where this is not a dynamic control, but a robot moving to any point. What we are interested is that how the robot can go to any point through visual guidance. So, this is a little different aspect of control. Okay. And again, after these two classes we will start again the some of these direct adaptive control schemes for robot manipulators, as well as we will introduce a nice an experimental setup that we have in our lab here, which is called, we say, inertial wheel pendulum. That also we will be discussing. Thank you.